In this video, I'm going to be proving why root 2 is irrational. In other words, why it's an irrational number. So, before I get into proving this, let's try to understand what rational and irrational numbers are. Let's start with rational numbers. They go with the symbol Q that represents all rational numbers, Q for quotient. A rational number is a number that can be expressed as a fraction, P over Q. So we have P over Q, where P and Q must be integers. This is critical. Many don't understand exactly what rational numbers are, but rational numbers are expressed where there's a numerator that must be an integer and a denominator that must be an integer. So these have to be integers. And Q cannot be 0, of course. But these must be integers. For example, 4 over 3 is a rational number because 4 is an integer and 3 is an integer. So is 3 over 1. 3 is an integer and 1 is an integer, so therefore 3 over 1 is a rational number. But root 2 over 3, for example, is not a rational number because root 2 by itself is irrational. Root 2 is not an integer. 3 is an integer, but root 2 is not. So therefore root 2 over 3 is not rational, and I'm going to show you that root 2 is irrational. So irrational numbers are shown with the symbol r slash q or r minus q or q with a dash on top, with a hat. So all it's saying is that irrational numbers can be expressed as real numbers minus rational numbers. Real numbers, the set of real numbers minus the set of rational numbers will give you the set of irrational numbers. So again, a real number includes all rational and irrational numbers, okay? So now we know the notation and for the sets for irrational numbers. What is an irrational number? It's a number which cannot be shown in the fractional form P over Q, where P and Q are integers. In other words, as long as you don't have an integer in the numerator or an integer in the denominator, you're going to have an irrational number. Okay, some types of irrational numbers are pi, e, and root 2. So another property of irrational numbers is that they have decimal expansions that don't terminate. In other words, the expansion goes on. And furthermore, irrational numbers have decimal expansions that are also not periodic. In other words, you're not going to see sets of numbers repeating over and over again. Like, for example, 3.333. Okay? Let's now start with the proof of what root 2 is and why it's irrational. Well, how do we get root 2? The Greeks figured out a long time ago. If you have a right triangle and each side is of length 1, well, you can measure the hypotenuse. It's going to be this funny number, which is going to be the root of 2. Let's just do the simple Pythagorean theorem. You have 1 squared plus 1 squared will equal the hypotenuse squared. Okay, so that means we have the hypotenuse squared is equal to 2. And the hypotenuse will now equal the square root of 2. Obviously not minus root 2 because we cannot have a negative distance. Okay, so that's what root 2 is. Now let's show that root 2 is irrational. For this, we're going to use a method of proof called proof by contradiction. Now, I highly recommend that you review proofs. This is not a course on proof by contradiction. This is showing why root 2 is irrational. So we're going to use proof by contradiction. And we're going to assume that root 2 is a rational number. In other words, we're going to assume that root 2 is equal to a over b, where a and b are integers. We're going to assume that root 2 is rational. And then we're going to show that this is an incorrect assumption. A over b is in reduced form. In other words, we cannot cancel the numerator and denominator any further. A over b is in reduced form. So that this has a special property. When a over b is in reduced form, that means that either a is odd or b is odd. For example, 4 over 14. That is equal to 2 over 7. You'll notice you'll always have one even and one odd or two odd numbers when it's in reduced form. We can't have two even numbers because we can just divide by 2 in that case. All right? So if root 2 is equal to a over b, then clearly, let's write this down again. Root 2 is equal to a over b. That means that 2 is equal to a squared over b squared, which means that a squared is equal to 2b squared. If a squared is equal to 2b squared, that means, and this is from number theory, you must review a little bit of the number theory. If a squared is equal to 2b squared, that means a squared must be even. So a squared is even. A squared is an even number. A squared is even. If a squared is even, then a must be even. If a is even, then a can be written as 2m. Every even number can be written as 2 times some other number. And now we're going to substitute 2m for a squared. So now we're going to have 2m squared is equal to 2b squared, which means that 4m squared is equal to 2b squared, which means that b squared is equal to 2m squared. So now this means if b squared is equal to 2m squared, what does that tell us about b squared? It must tell us something very important about b squared. If b squared is 2 times some number, m, and we must say again that m is an integer. Okay, b squared is equal to 2m squared. That means b squared is even. B must be even. So if b squared is even, then b must be even. But we have a problem because we said that a over b was in reduced form. But since a over b is basically an even number over an even number, therefore it's not in reduced form. Therefore root 2 which equals a over b, must be irrational. And this completes our proof. Thank you.